All right, class, welcome back. I didn't finish this, but I have to finish this. So here it is. As we discussed in class, in period 7 at least, we can take a proof and convert it into a number. So in case you didn't understand this thing that we did earlier in class or earlier in the video where we were doing a coding, because I didn't explain it very well and I was like shouting and jumping up and down, this is an explicit example of this. So we will understand this coding scheme, and we will also see that there are a countable number of symbols, or a countable number of proofs rather. Okay, so take some very specific syntax for first order logic. We've actually been quite casual, but insist on some extremely tight rules regarding precisely how you have to write out every single sentence. And focus your attention on specifically piano arithmetic. And piano arithmetic is just the first order logic formalization of basic arithmetic of natural numbers. And it has only a couple of basic symbols. 0 is the undefined term of piano arithmetic. The successor function, we have a binary symbol for addition and a binary function symbol for multiplication. We probably also want the less than symbol, I just realized, but who cares, because I'm not going to use it right now. So like if you were doing this for real, you might want some more symbols, but I ran out of space. Then you also have the basic symbols that are required just for logic at all, like comma, left paren, right paren, and or arrow, biconditional, not, bottom. For all there exists. Maybe you want more symbols, maybe you want an XOR symbol, maybe you want fewer. We have always equality as well in any first order logic. Okay, now I've added in some special characters. This is the tab in symbol for fit style proofs. This is the tab out, and this is the new line character. And then we have, if necessary, who knows how many variables you might need. So we are going to give ourselves a countable number of variables. So really this should be like x1, x2, x3. So this list goes on forever, but I'm too lazy to do that, so I'm just going to call it x. Okay, this is what's called a code. And now we're going to do a proof. And the proof we're going to do is a proof that you've done before, or you've done something like it before. It's the proof that not for all x, x equals 0 implies that there exists an x such that not x equals 0. Okay, so I'm actually not going to use addition, multiplication, the successor function, or anything. I'm just going to, but this is certainly true. It says if it's not true that everything is 0, then something is not 0. Okay, so it's kind of like a little bit stupid, but it is a theorem of piano arithmetic. You can do a proof of this from the axioms of piano arithmetic, and using the rules of first order logic, you can prove this theorem. In fact, I'm not going to use any axioms of piano arithmetic because this is just a law of logic alone, but I am using the language of piano arithmetic, specifically 0, so this will count as a theorem of piano arithmetic, something you can prove from the axioms. Okay, let's just do the proof really quick. Okay, and this will be a little bit of a practice on Fishtail proofs. I feel like this is the hard version of 42. So let's go. What are we going to do? We're going to assume that not for all x, x equals 0. I would go to 2 times speed now if you were in my class. And I need to show that this is true. So I have to do it by contradiction. So I'll suppose that it's not the case that, that it's not the case that for all x, not x equals 0. I probably want like more parentheses in there if I was doing this for real, but like I'm not doing it for real. Okay, now what? All right, because I'm so good at this crap, I sort of know what to do next, or at least I think I do. Oh, you know what I just realized? I probably need like some more things. Nah, never mind. Okay. I'll just keep going. I'll just make this work somehow. Okay, so now what am I supposed to do? I'm supposed to do that everything is 0. So I'm going to take an arbitrary element. Let's call that arbitrary element x. Okay? And so let me just abuse this notation slightly. I'm just going to put an x here. Okay, great. And now, what next? Now, I'm going to show that x is not, that x is 0. How am I going to show that x is 0? I'm going to suppose that it's not. So here in line 3, I'm going to suppose that it's not the case that x is 0. But now, if it's not the case that x is 0, that means that there exists an x such that x is not 0. And therefore, maybe I use a different letter here. Maybe I use y just to kind of keep it a little fresh. So take an arbitrary y, show that it's not the case that y is 0. Well, that means there exists an x such that x is not 0, because existential intro from that, sure, but that contradicts, because now there exists an x such that x is not 0, and there does not exist an x such that x is not 0. Such that x, yeah, and that is a contradiction. Hence, what have we just proved? We've just proved not y is 0. In other words, y is 0. But having proved that y is 0 from nothing, I now conclude that for all y, or for all x, x is 0, but that contradicts line 1, so I have for all x, x is 0, and not for all x, x is 0. So that is a bottom, and thus I get, I'm going to run out of room, I get not there exists an x such that not x is 0, and so there exists an x such that x is not 0, and so final conclusion is not for all x, x is 0, arrow, there exists an x, not x is 0. Okay, good. That took hopefully only 5 minutes. That is a proof, as we've come to expect, of this basic fact. I skipped the reasons because they're not really part of the proof. Now I'm going to take the crazy move of coding this proof. And hopefully I'm going to do it correctly. I'm going to code it by writing it as one long string. So we start, and I guess man, I don't even know. I guess I start with a new line, tab in. So it's if you guys were all here, I would have you call out what to do. But it's new line. So starting here, it's new line, tab in, skipping the numbering also. And then it's just not for all x, paren x equals 0. Followed by new line, tab in, not, there exists x, not, this is just ridiculous. I can't believe I'm doing this. Boom, then followed by new line, tab in, then y, then new line, no, it's new line, tab in, y, new line. I'm probably even just messing this up. Then tab in again, then not, paren, y equals 0, paren, new line. I'm going to just stop in a minute because this is terrible. X of not, paren, x equals 0, new line, all right, etc., etc., etc. Okay, I think I've proven my point, which is that there are a finite number of symbols of basic first-order logic. There are, at least for this language, the language of piano arithmetic, a finite number of symbols. There are a countable number of variables, if you need that for some kind of reason. And there are a probably some handful, maybe I need even more, special sort of character symbols. But I can certainly take my entire proof and convert it into one long string. And what's important to realize is that this string is finite. It is a finite string. And now what I'm going to do is this thing, I didn't explicitly say this, I think, in class, but what we're going to do is this thing called Gödel number. Gödel, greatest logician of all time, and someone who's going to dominate this class for the last like 2 weeks of it in January. Famous for Gödel's completeness theorem and Gödel's incompleteness theorem, which we're going to learn about later. But what he did as an aid in these proofs of his was to come up with this ingenious coding scheme in which strings of symbols, as we've seen here, can be converted into numbers. And what we have first here is a code, and so now I will convert this into the code. So 18, oh my god, 9, 11, 21, and maybe commas here are good. So this like 3, 21, oh man, 13, 14, 4, this is 20, whoa, it's 4 again, 4 is paren, then the new line character is 20, and now I'm right here, I'm kind of running out of space. This is another 18, okay, I'm going to quit a little bit earlier in each one of these steps, but hopefully everyone sees that this proof, any theorem of piano arithmetic, is a theorem which has a proof from the axioms of piano arithmetic. Any proof must be finite. That's built into the very nature of what it means to be a proof. So every one of these finite proofs can be converted into a finite string. Every one of these finite strings can be converted via this coding scheme into a finite sequence of natural numbers. And now the part where we Gödel number is we convert this sequence of code numbers into one giant number. And the one giant number is 2 to the power of the code number of the first character in the proof times 3 to the code number of the second character in the proof times 5 to the 9th times 7 to the 11th times 11 to the first, 13 cubed, 17 to the 21st, 19 to the 13th. This might be just blowing your mind and how outrageously large this number is. Let's see, what about 21, 13, 14, 4, 20, 18, and this is just going to keep on going. That was that last time, and there was like not, there exists, or like the next two, right? 9, 12, et cetera, et cetera, et cetera. Okay, what I have now constructed is a one massive, gigantic number. Let's see if we're even on frame. Yeah. This one massive, gigantic number captures in its entirety all of the information of this proof. Because, first of all, you need to know a bunch of background pieces of information, like there are an infinite number of prime numbers. Every number is uniquely decomposable into a product of prime numbers. So we're to eventually finish this massive number. When I'm going to get to some number, it's going to be like, 10 to the who the hell knows, hundreds of whatever, gigantic, massive thing. But it can be prime factorized all the way down, expressed as a product of prime numbers. And there are algorithms for this that will end in some finite period of time. And thus giving me this prime factorization. Then I read off the code numbers, or I read off the powers of the prime factorization, these numbers, which gives me this unique sequence. I'm explaining the decoding scheme now. I did this in the 7th period as well. This decoding scheme can, via this code that we established, be used to reconstruct this string, and this string is just a proof. What this means is that there's this entire process describes this sort of function. And what this function does is it takes proofs of theorems of piano arithmetic. It's actually a little bit redundant even, because we define a theorem of piano arithmetic to be anything which is provable from the axioms of piano arithmetic with the Fichte proof to the natural numbers. And this is, in fact, this is an injection. And it's like almost a bijection. What this proves is that the set of theorems of piano arithmetic are a subset of the natural numbers. And so our conclusion is there are only a countable number of proofs. Okay, the reason why this is so incredible, and I think you don't possibly, you don't appreciate it until you kind of spend / you might call this waste some time getting into the exact details of it. What you then sort of appreciate is that I can now enumerate every single proof of piano arithmetic. During period 7 we talked about an infinite number of monkeys and an infinite number of typewriters making the works of Shakespeare, producing all the works of Shakespeare. In fact, I need just one monkey and one typewriter, and I just need a really, really long, and I don't need an infinite amount of time. I need just a very, very, very large amount of time. And what I can do is simply go through every single natural number in order. Take that natural number, decode it into take that natural number, factor it into a product of primes, convert that into a sequence of natural numbers, convert that sequence back into a string of symbols from my alphabet, and then take that as the proof. And okay, the problem is that the vast majority of numbers are not going to be valid proofs at all. Take the number 12, for example. Well, what is 12? It's 4 times 3, so it's 2 squared times 3. So presented with 12, I would decode it as 2 to the 2 times 3 to the 1, and thus I would decode it as the representing the sequence of natural numbers 2, 1, which I would then decode as comma. Oh no, I didn't even use 1. That kind of sucks. Here, let me do 36. That's better. No, let's 72. Let's be bold. 72 is 2 cubed times 3 squared. Okay. So that is going to turn into the sequence 3, 2. And what is 3, 2? It's left paren comma. The greatest proof ever. So left paren comma. Okay, of course that's not a proof. So probably like 99.9999999% of natural numbers, when decoded, are going to be not valid proofs at all. But within that set of natural numbers will be every single possible proof. And so we can sort of create a machine that just churns out decodings of natural numbers, and it will eventually stumble upon every single possible valid proof of piano arithmetic. What's required now is some other mechanical procedure which will somehow go through these strings of symbols and determine whether in fact they are valid proofs. But that doesn't sound like it should be so hard actually, and because we've defined what it means to be a proof very carefully as this sort of syntactic relation. And so somehow I can now prove every single fact of arithmetic. As long as I'm willing to wait a very, very long time. Okay, good. We probably have 5 more minutes or something and left of stuff to do. The one thing that I skipped in period 7, so going a little bit out of order now, is to flip back to page 5. Maybe I'll just erase things easier. If I go back to page 5. Sorry about all this video watching, but Gotta get the class in order for Reynolds. Okay, so page 5, and in the past I always assigned these problems as homework, but then like no one got them anyway. So I don't know, you can try for a minute, because these pages are actually pretty intuitive. So number 7 says, prove that the set of points on the real number line, in other words, the entire real number line, prove that the set of real numbers is equinumerous with the set of points on the semicircle. Okay, so I guess what do I even do? This is like the set of points x comma y or something, such that what the hell is the semicircle? Radius a half, and it has yeah, it's like x minus a half. Am I doing this right? Over 1/2, up 1/2. Yeah, x minus a half squared plus y minus a half squared, like equals like a half squared or something like that. But that's not even totally correct, because I also want it to be true that x is between 0, strictly between 0 and 1, and y is between 0 and 1 inclusive. Okay, that might be like a little bit overkill, but if you take that's basically what's written on the paper, right? There's this just picture. Okay, this whole problem is really just meant to be done with picture. We have this point 0, 0, this point 1/2, this point here, this point here, and this point here, and there's just this semicircle, man. And the idea is that we make open circles here and here. Okay, goal, show that every point on this semicircle, not including the endpoints of the semicircle, show that that set of points is equinumerous with all the real numbers on the entire real number line. That's what this is saying. Show that there's the same number of real numbers that there are points on this semicircle. Well, I think it's just totally obvious what to do, and I gave you a hint anyway. Put a light bulb at the center of the circle. In other words, just go here, and now just, okay, proof by picture, just kind of like shine rays down to the, pretty cool, wherever that hits, cha-cha-cha, cha-cha-cha, is a real number. And so I have established a bijection by mapping so this is now the entire, imagine the x-axis to be the entire real number line for every single point on this semicircle, like match it to, in a one-to-one bijection, with the real number on the x-axis that it's collinear with this center of the circle. So match this point with this point, match this point with this point, etc. Okay, so for every point on this semicircle, there is a real number. For every real number, there is a point on this semicircle. Simply connect that real number to the center of the circle and match it with the point. Okay, maybe some geometry theorems or something required to show that this all works, but I think that's pretty clear. Okay, so now comes part 2. Which is number, I guess it's number 8, says, okay, now prove, can I call this set something? Let's call this set like A. The number, let's call this set SC for semicircle, okay? So that was fun. Now, prove that the set of points on the semicircle is equinumerous with the real numbers in the interval 0, 1. In other words, prove that the set of points on the semicircle is equinumerous with the real numbers between 0 and 1. Okay, well, you just take this same picture, and now you just drop down, man. So you just say, all right, from each point on the semicircle, you just like drop. So to each point on the semicircle, match, and this is a bijection intuitively to some point on the interval 0, 1. So every point on the semicircle lands somewhere on the interval 0, 1, and every point on the interval 0, 1 lands somewhere on the semicircle. Okay, so now, by some like kind of meta theorem of bijections, here's what we have done. In class, we showed that the power set of the naturals was uncountable. Then we showed that we constructed a bijection between the power set of the naturals and the real numbers between 0 and 1 by using the binary expansion. Then I showed over here that there are, in number 7, that the real numbers are equinumerous with the points on the semicircle. Then we showed that the points on the semicircle are equinumerous with the real numbers on the interval 0, 1. And so by some transitivity of equinumerosity, in fact, all of these are equinumerous with each other. Conclusion, there really are the same number of real numbers as there are subsets of natural numbers. So this to me is the most elegant proof of this fact. This is usually what most people do. They map the power sets of the naturals to the interval 0, 1, and then you map the interval 0, 1 to all the real numbers. And there are more formal ways to do that with, like, I can't remember, arctan or some crap like that. All right, last thing. This number 9 says, prove that the set of points on a line is equinumerous with the points of the plane. All right, this is kind of insane. What this is basically saying is that R is equinumerous with R cross R. Now, if you put it like that, then maybe that's not quite so shocking because we saw that N was equinumerous with N cross N. But, dude, this is shocking if you think about it geometrically. If you actually care about things like understanding the geometry of the situation, then this is mind-blowing. This sort of shows somehow that there are the same number of points on a line as there are points in the entire plane. And that is somehow, it was extremely difficult for the 19th century mathematicians to accept. Even in the age of rigor, they felt somehow that like the geometry of like dimensionality was was coherent, and that somehow that there were just more points in the plane than there were points on the line. And the proof of this is a little maybe like disturbing or something, but it makes total sense. So take an arbitrary, what I'm going to do is I'm going to show that these two are equinumerous by constructing an explicit bijection. So take some arbitrary point x comma y, this is some real number. Well, what the hell is this saying? Oh, then using previous methods, let f map this point x comma y. No, sorry. Let f be some function which takes any real number and gives back a number in the interval 0, 1. So let f be a function which takes you from real numbers to the interval 0, 1. Okay, we've seen already that that's not so hard to do because the real numbers in the interval from 0 to 1 are equinumerous. Okay, well if that's the case, then what happens when I plug x into f? Well, I'm going to get some real number between 0 and 1. So let's call it 0 point, like A1, A2, A3, A4, etc. Let these be the digits in the decimal expansion of the x coordinate, so to speak, of my point. And let y be, or let f of y be 0 point B1, B2, B3, B4, etc. So these are the digits in the decimal expansion of the real number between 0 and 1 that f converts y to. Okay, and now I somehow need to combine these 2 points into 1 point. So then create a new function g which takes this ordered pair and shuffles the digits. So let it be 0.A1, B1, A2, B2, A3, B3, etc. In other words, G is a function which takes this ordered pair of real numbers, which might be very large or possibly negative, who knows what, and using the f function, first converts these two numbers into real numbers between 0 and 1, and then shuffles those real numbers to give you another real number between 0 and 1. And what we have just therefore shown is that R cross R is equinumerous with just the real numbers between 0 and 1. Because we have constructed a mapping in several steps, which takes an ordered pair, converts each member of that ordered pair to a number between 0 and 1, shuffles them together into a single number between 0 and 1, and I guess if you wanted to, you could even do the final step, but I ran out of space, to then convert back from a number between 0 and 1 to a real number by taking the interval from 0 to 1, going up to the semicircle, and then going back out to the real line. That would be the completion of the direct bijection between R and R squared. What this means is that there really are the same number of points on a line as there are points in the plane. And this was very disturbing. This broke the kind of last, one of the last pieces of sort of intuition that the 19th century mathematicians had about geometry, that somehow lines were composed of points and planes were composed of lines in some kind of sense. And Cantor, when he proved this, wrote a letter to his best friend Dedekind about it, of course, and said in this letter, I see it, but I don't believe it, or something like that. That's going to be a paraphrase. It's one of these other lines which have sort of entered the a list of famous lines in the history of mathematics. Okay, woo! We are basically done. I'll say one more thing, which is that in that same decade, basically, following up on this kind of work by Cantor, Peano, who was also sort of on the cutting edge of these things, constructed what was called a space-filling curve. So to completely break the intuitions that the rest of the normal 19th century and 18th century mathematicians had about dimensionality, Peano constructed a curve which, in a linear fashion, in some sort of fractalish pattern, would go through and, okay, this is going to be the worst space-filling curve ever, but via some kind of jump, filled up the entire square. And this curve would now just sort of go on forever, and you could prove, wow, that's bad. Peano could prove that with this sort of single parameter, so to speak, this one-dimensional object, this thing that we just call a curve, that you think of as being fundamentally, in some deep sense, one-dimensional, Peano could prove that eventually this curve would cross through